Well, good morning, everybody, and hope everyone's doing well. Yeah, I mean, I guess people that are working from home, it looks like are going to continue to work from home for a bit longer. So yeah, I'll see whether I've got enough content for the talk to take us through the winter months. Certainly got plenty more to talk about. So yeah, I'm set for the next couple of months at least. Yeah, we'll just have to see say how much other topics I can find to talk about, and say maybe we can running throughout the winter as well. So today's topic is frictional losses. Again, I've split this into different parts, so this is going to be part one, just to keep the presentations fairly short. 20 to 30 minutes really for each presentation, just to kind of keep it quite snappy. If you're joining us for the first time, so hello and welcome. Thanks for watching. There's quite a back catalogue of these presentations now, but though I keep realising that I haven't updated the number again. So this is presentation 21 rather than 20. Yeah, apologies for that, but yeah, this is presentation 21. All about frictional losses. So this is one. So a good place to start is what is frictional loss? So obviously, friction is something that affects everything in a mechanical sense. That's why we have oil in our engines, is to make things more efficient. That's why we want to have grease on our door handles and door hinges, because often friction is the enemy, really. Not always, but most of the time friction is the enemy because it makes things less efficient, because we have to fight against the friction to actually achieve what we want to achieve. Obviously, automatic fire sprinkler systems, we're all about getting water from point A to point B down a pipe. I suppose an interesting question is whether water rubbing against itself is completely frictionless. I'm not sure. I did give that a quick Google, and as per usual with those sorts of in-depth questions, I got a variety of different answers, so I'm not quite sure. But definitely when water comes into contact with other things other than itself, and most of the time in terms of sprinklers, we're talking about the water hitting the side of the pipe, then it will create friction. The roughness of the pipe, the surface in which the water is hitting, is effectively slows down the water, kind of trips it up as it hits the side, which then in turn reduces the pressure and also creates a whole load of different kind of currents and change of direction, and all of that is going to affect the pressure within the pipe. So that's frictional losses is down to friction that is created as the water goes from point A to B. So just keeping it about pipes for the moment, the amount of friction created depends on the size of the pipe and also the smoothness of the pipe. So even plastic pipe, which to our eyes looks completely smooth, of course, if you look at it under a microscope, it isn't. It's got lots of bumps and ridges and texture, which obviously going to affect water flow. But different materials are going to have a different smoothness. The smoother the pipe, the better. But it's all going to create some friction. As I say, larger pipes cause less frictional loss than smaller pipes. And the reason for that is because as a kind of a percentage-wise, there's less water touching the sides. There's more space in the middle for the water just to run along and be with itself rather than to touch the sides of the pipe. We've got an example there for you on the right-hand side of the screen with a 32mm pipe and a 50mm pipe. And what I've done is I said, okay, well, I've calculated the area, I've calculated the perimeter, and I've divided one by the other. And I've said that essentially the perimeter, the percentage of the perimeter of the 32mm pipe is about 12%, and a 50mm pipe is only 2%. Okay, so again, it's not 100% scientific, but you get the idea that the bigger the pipe, the more space you have in the middle, and therefore there's going to be proportionally less water touching the sides, and therefore you get less frictional loss. But that's not the only time that we have frictional loss. Basically, everything that affects a smooth water flow is going to create frictional. Again, in an ideal world, when we go from point A to point B, it will be in one straight, continuous run of pipe, because that would give us the least amount of frictional loss. But of course, it isn't like that. We're going through elbows and T's. We're going up, down, left, right, and we also go through various fittings like elbows, T's, valves, etc. And all of these are going to add additional frictional losses, because of the sort of increase and decreased pipe size. But often when you go through a valve, the water actually kind of gets squeezed a little bit as it goes through the valve and then can accelerate back out the other side. Also, the way in which the pipework is actually fitted together is often going to cause more obstructions within the pipe. So again, like a groove coupling, for example, just have that little kind of bump now on the inside of the pipe. Plastic components, again, they're going to be a change in internal diameter as we go through different fittings. All of that is going to cause the water to have these kind of lots of different currents and things, which are all going to slow things down, because the best way of doing it is just to have a nice, long, straight piece of pipe. As soon as we're not doing that, then we're creating additional movement in the water, and again, that's going to cause additional frictional loss. And this is all very, very complicated as far as actually understanding and calculating exactly what is going on the inside of a pipe. I'm a Formula One fan, and that they spend so much money trying to understand aerodynamics. They're trying to understand how the air is going to pass over the car, so they have lots of computers telling them lots of information. But even with all that computing power and all that budget, they don't always get it right, because conditions are always going to change. The wind's going to come from a different direction, different speed, the temperatures around. So there's loads of factors. It's very, very difficult to calculate. So there are various software packages out there that will look at calculating frictional losses, but they're all based on assumptions, a little bit of guesswork, and so everything is an estimate. It's an approximation of what actually is going to happen in real life. Frictional loss is different to gravitational loss. In the sprinkler industry, we call this static head, which is a force required to overcome gravity. So we've got two different types of losses we've got to allow for: frictional loss and static head. The static head, say, is the gravity effect. Again, going back to our science lessons at school, which I often do, if you have that kind of beaker and you punch some holes in the side, then you should know that the water will come out in kind of a different rate and different pressure at the bottom of the beaker than it does at the top. That's because of the pressure pushing down creates a higher pressure at the bottom than at the top. And it's kind of the same thing in reverse. If we've got a pump pushing the water into the bottom, then we're going to get more pressure at the bottom than we do at the top, because as the water goes up, we've got to start fighting against gravity. So we are going to lose some pressure going up that way. So water, again, pure water, 1 cubic meter weighs a ton. So we can kind of look at that and look at the gravitational energy, and we can say that we're going to lose roughly 0.098 bar of pressure per meter, i.e. 10 meters is roughly 1 bar. Is that right? Yeah, that's about right. So yeah, that's kind of a kind of rule of thumb that we can apply when we're looking at static loss. But as I say, the focus of this presentation is all about static loss. So another question to answer here: why does frictional loss actually matter? Well, that's because we're trying to balance lots of different things here when we're doing sprinkler calculations. A really important one is ensuring that every sprinkler head has the minimum operating pressure. Okay, so for ordinary hazard groups, this is typically 0.35 bar, but again, it would also depend on the data sheet supplied by the sprinkler head manufacturer. It may vary, but yeah, 12845 states that ordinary hazard occupancies must have at least 0.35 bar per sprinkler head. And that's important because the way in which the water hits the deflector, the distribution of the water, basically the sprinkler head is not going to do its job properly unless it gets 0.35 bar at the head. So that's something we need to bear in mind. A lack of pressure is going to be a problem. Overpressure can also be a problem, but most of the time what we're doing with these calculations is kind of making sure that we reach the minimum rather than worrying about the maximum. But so we do kind of have to look at both as well. The size and expense of sprinkler pipes. So as we mentioned earlier, larger sprinkler pipes have got less frictional loss than smaller pipes. So, one solution is just, okay, let's do 200 millimeter pipes, nice big chunky sprinkler pipes, just use them everywhere. We could do that, but of course we need to balance the fact that those pipes cost more. But I think probably more importantly, they take up a lot of space. Riser sizes, void spaces, everything is being squeezed and squeezed and squeezed. So yeah, we don't want to oversize our sprinkler pipes. We need to just work out what is the minimum size that is going to work with the calculations that we've got. Size and expense of sprinkler pumps. So again, another solution is have a really big pump which is going to deliver lots and lots of pressure. That way we can overcome all of the frictional resistance. So we could have really, really small sprinkler pipes everywhere and a really big pump. Well, first of all, that's not going to work because we need flow as well. And so again, larger pipes are going to help with the flow. And also we need to balance the cost of the fire pump. And so again, we don't want to oversize, over-engineer things. So we need to look at what is what's the best solution to meet the minimum requirements. Size and expense of sprinkler tank. Again, if you don't get this stuff right, then you're going to end up with a much larger sprinkler tank than you would necessarily need. That's because again you would work out, well, these sprinkler heads are going to allow for these to operate. If you've oversized everything, then you're going to get more water out of those sprinkler heads. You still need to meet the minimum duration factor, so that could be 60 minutes. So you'd end up with a bigger sprinkler tank because you've oversized the pipes in the pump, for example. Allowing a little extra for changes. So again, with all these calculations, if let's say for argument's sake, we're looking for the number 100. So 101 would be an acceptable answer to this kind of problem, but we want to allow a little bit of room for error because things change. When we get onto site, walls change, doorways change, different services are kind of maybe not what we're expecting them to be, or things have to change because a problem's been found. So as a sprinkler designer, we need to make sure that there's enough sort of slack in the calculations to allow for a few extra elbows and a little bit of change of pipe size just to overcome sort of practical differences on site. We don't want to be just stuck in our sort of computer world and saying, yeah, that's exactly the solution we need. Make sure that it's going to work real life as well. So we've got to balance all of these things and say a frictional loss is what we're trying to work out in order to make sure we get an efficient system. How do we calculate frictional loss? Well, so as I mentioned a few times already in these presentations, there are two main ways of doing this. What we call table or pre-calculated method, or FHC, full hydraulically calculated. The difference being, say, table or pre-calculated. Pre-calculated is a good way of describing it. What we're using is basically half of the job has already been worked out. So we can just kind of add in a few sort of particulars from the project that we're working on, and that we will get a reasonable answer, or we will get a compliant answer based on the calculations that have already been done in advance using various assumptions, which all mean that we get, say, a suitable answer. If we go for full hydraulically calculated, essentially what we're using is a computer program, and we're working out the frictional losses everywhere. We're working out the pressure everywhere, and we can actually see the pressure at all the different heads. And because it's a computer model, once we've built it, we can then sort of interrogate it. We can say, okay, what happens if I swap this pipe over? What if I use this size instead of this size? If I add an extra elbow here, what effect does that have on the calculations? So we can kind of fine tune it, get it as efficient as we can. Table method is a lot quicker. FHC is kind of more adaptable, editable, and we're allowed to fine tune it. So what I'm be talking about now is mostly, I'll be talking about pre-calculated table methods, but the FHC is doing the same thing kind of in the background as all a computer program. So just a reminder that this is what we're interested in. So this is what the pre-calculated nature is based upon. Most unfavourable location, most favourable location. The most unfavourable location is the area that's furthest away from the fire pump. So what we're saying here in this instance is if the sprinklers in the furthest area have got sufficient pressure, then everywhere else should be good. Okay, we're looking at the worst case scenario, pressure at the sprinkler heads. So as long as they're happy, all the others will be happy as well. Also, the most favourable location, and I say that is to do with the water storage tank, because the worst case scenario as far as the pump is concerned is the most unfavourable location. The worst case scenario as far as the tank size is concerned is the most favourable location. There's going to be more water coming out of those heads, therefore we need to allow for the duration factor. So FHC will work out the pressure at every single head on the system and then test that for yourself. For table or pre-calculated methods, we also use design points. So again, we're kind of simplifying it down. We're looking at, normally it's kind of 17, 18 heads back. Choose a point and say, right, that is a design point now. And then we can work out frictional losses to that design point rather than all the way to each individual head. Again, it just saves us time. It simplifies it down. It gives us a kind of a head start in working out these calculations. So this is the kind of question when you do your kind of sprinkler exams. Basic and intermediate exams, this is the kind of question you'll be looking at. So you've got design points, and you'll be working out the frictional loss from the design point back to the alarm valve. And you're allowed 500 millibar, which is half a bar of frictional loss between the C gauge and any design point. So when I say loss there, you need to take gravity into account as well. So that's frictional loss and static loss. And yeah, that might sound quite hard. 500 millibar is not a lot, but say if we increase the pipe size, we get quite a lot of difference in the amount of frictional loss. So say going from 100 to 150 does actually make quite a big difference in terms of the amount of frictional loss that's created. So it can be done fairly easily. But yeah, that's the criteria we're working at. So as long as we do that, then all of the other calculations will basically take care of themselves and get a compliant design. So what are we actually doing when we're calculating frictional loss? Well, say every method of working this out is going to be an estimate, an approximation. So there are lots of different formulas which you can choose, lots of different models that you can choose. In the sprinkler industry, we tend to use the Hazen Williams formula. Like I say, no formula is perfect. In general, the more complicated the formula, the better answer you get. But obviously, the more work you've got to do. So yeah, the Hazen Williams formula is a good compromise between complexity and accuracy of the answer, but complexity at the same time. So here it is, and let's just go through it. So P is the pressure loss in the pipe in bar. On the top of that line there, 6.05 times 10 to the 5 is a constant. That's just a number. We have Q, which is the flow through the pipe in litres per minute. So as the flow increases, frictional loss will also increase. Makes sense. D is the internal diameter of the pipe, millimeters. Okay, so again, the bigger the pipe, the smaller pressure, because D is on the bottom of that section there, so that's a dividing thing. C is again a made-up number. It's a constant, and that's for the type and condition of the pipe. So essentially, we can adjust that number to reflect the fact that old steel pipe is going to be rougher than new steel pipe, and plastic pipe is going to be smoother than both of them. So again, because C is on the bottom of that part of the equation, that the bigger the number, the better. So again, smoother pipe has got a higher C value than. L is the equivalent length of pipe and the fittings. So I'm going to pick up on equivalent length in another presentation. For the moment, let's just call it length of pipe. Okay, so L is the length of the pipe. The longer the pipe, the more frictional loss we get, because there's more pipe in order for the water to bash against. Again, kind of all makes sense. So let's do a little calculation. Let's calculate the pressure loss for a 2 meter length of pipe. The pipe is 100 millimeters of nominal diameter, and the flow rate, we're going to go for 1,000 litres per minute. Now that's quite a lot, 1,000 litres per minute. But again, in the sprinkler industry, in terms of doing these calculations, we tend to use 1,000 litres per minute as a figure, so we don't, because often we won't know what the flow rate is without kind of doing further calculations. So going for 1,000 litres per minute kind of covers us really. It's a reasonable number to use. It's probably on the high side. So that kind of covers us for that kind of calculation. So we put some numbers into the equation. So P, that's what we want to know. That's what we're trying to calculate. Q, say we're going for 1,000. D, remember that's a nominal 100 millimeters. Again, it wouldn't make a massive difference in this calculation, but actually, the internal diameter 105.3. So there. D, so for mild steel, we use a value of 120. L is the length, 2. So we can bash all of that into a calculator, and it will spit out an answer. 8.6 times 10 to the minus 3 bar, i.e. 8.6 millibar. Okay? 8.6 millibar is the frictional loss experienced from getting water from one end of a 2 meter length of pipe to the other end of a 2 meter length of pipe. And so you can obviously change that for different diameters, different lengths, and it will always just spit you out an answer. However, we have a simplified formula. So again, table methods, we are simplifying it down because that's quite a lot of numbers. There's quite a lot of variables. It would take quite a long time to kind of work through that equation. We can actually simplify it down, and we're simply going to say P, the pressure loss, equals K times Q to the 1.85. Power 1.85. So that's staying the same. You notice that Q was there at the end. Q, the flow rate, power 1.85. So that's still there, and everything else has been condensed into K. So P now is what we want to know. Q is, say, for ordinary hazard calculation, we use 1,000 litres per minute. So again, that Q to the 1.85, that becomes a known number from that point on. And K is a constant for the given pipe diameter and roughness. Okay, so C value, again, generally speaking, in sprinkler systems, we're going to be using steel. So again, that kind of becomes very, very similar. And we can use K, which has already been calculated as a frictional loss per meter of these different types of pipe. So you can see on this little table here, so a 65 diameter sprinkler pipe will have a loss of 35 millibar per meter, 80 is 16 millibar per meter, 100 4.4, and 150 0.65. So again, you can see from that table there that increasing the pipe diameter makes quite a big difference in terms of the frictional loss we experience. Okay, it's going from 100 to 150, going from 4.4 to 0.65. So again, makes quite a lot of difference. So hopefully you're kind of still with me on this one. So, so using our simplified method, then we just do K. Written it the wrong way around here, but we've got K, which for 100 millimeter pipe number is 4.4. Okay, and then we've got to times that by loss. Just need to do the loss per meter, 4.4, times 2, which is our 2 meter length of pipe. We just do 2 times 4.4, and we end up with a frictional loss of 8.8. Now, if you remember back to when we did the full Hazen Williams equation, we got 8.6. Now, with our simplified method, we get 8.8. And again, that's all completely deliberate. Whenever we kind of simplify things, we're always going to kind of round it up, because more frictional loss than reality is safer, isn't it? If we're allowing for slightly more than we're actually going to get, then we're on the kind of the safe side of things. So when we're doing the simplified equation, we do get a slightly bigger number, which again kind of partly explains why FHC will give you will give you a lower answer, a more accurate answer, because it's basically using the Hazen Williams formula in the background to calculate all these different points, all the different heads. The simplified formula, we're always adding a little bit just in case. So coming up, I'm going to be looking at more equivalent lengths. We're going through what the different fittings are, explaining how we convert a frictional loss into an equivalent length, and I'll be going through some more in-depth calculations in terms of getting from point A to point B and calculating the frictional loss to kind of get there. So yeah, you can learn a little bit more about what's going on. But that was kind of a good starting point, a good introduction into terms of what is actually going on when we're calculating frictional loss in sprinkler pipework. Yeah, hope you found that useful and interesting. Next week we're going to be looking at high-rise sprinkler protection. So what is high-rise? I think is a good first question to ask. What changes do we make to our sprinkler system where we have a high-rise application? What are the kind of the special rules that we use, special equipment that you might see? for a high-rise building. Okay, so again, thanks a lot for listening. As always, I'm going to stick around and see if there's any questions and comments on that presentation. Otherwise, yeah, I will see you next week, Thursday, 10 o'clock. Remember, if you're watching this on YouTube, you can tune in live by following the links on our webpage, www.projectfire.co.uk/Sprinkler Talk. Yeah, I'm sure you can find Sprinkler Talk on our webpage. From there, you can join a kind of a sign-up sheet, and then you'll get a regular email update with a link to watch the presentation live. So yeah, I hope you join us live, doing so already. All right, thanks a lot for watching, and yeah, I'll see you next week.